Okay, good morning everyone. Uh, so this is the our third class today, and I will not be available at that 10 a.m. and from that 10 a.m. So I will just do the I will just record the class and send to you guys. So last time, what we have done so far, we were able to establish the targets. Um, of our ailment, which is the breast cancer, and then the target predicted the target of our plant, So far we now need to find out the common targets for both parties, and then we can go on with the rest of our analysis. But I realized that last time I forgot to talk about something. Um, for the target of the plant, actually, generally, what is done is that after finding out the different component, the different metabolites of the plant by the search strategy that we talked about last time, uh, we first need to study the drug likeness of the different metabolites. So is uh, w- so from there we will just need to use uh, the metabolites that are really respecting uh, that are actually uh, yeah, I mean that shows a drug likeness that can actually be used as drug. So we will see that today before we move on with the common finding out the common target. So this drug likeness, how do we do it? If you check the literature, there are different ways of doing it. But for us, we will be using how do you call it? We will be using Swiss ADMET. Yeah, so from there we will use what is called the Lipinski's rule of five. I'm sure you heard about that. So we will use the Lipinski's rule of five to find out the metabolite that are drug likeness and that can be used. So I will just explain it so that we know it, but we will not necessarily use our metabolite. I mean, even if because we have already fished out the targets for the metabolite, so we will just do it as for the purpose of knowing what we are actually talking about. So what I will now do. So let's go immediately on the website where we can actually find that. So we can go on Google, and on Google you will look for Swiss ADMET. Swiss ADME. So this is it here, Swiss ADME. So you will find the website is this right here, www.swissadme.ch. So we click on it. So this is the interface of the Swiss ADME we have here. So what we are going to do is, if we have our smiles, we put it here, we copy and paste it here, or if we don't have the smile but we know the structure we want to draw it, we draw it in Marvin JavaScript here, and then we convert it to smiles, and we will run it. So that means we will go back to um, our PubChem. So we know what we do in the PubChem. We are looking for the different smiles of our metabolites. So I will open my metabolites Excel file. All right. So I have gallic acid here. In fact, maybe we will just need to use the gallic acids only to just show an example actually. So garlic acid, we ask Bob can bring us garlic acid here. Garlic acid. And we will look for our smile. So this is the smile. Uh, Sorry, something happened here. I'm not sure about what happened right now. So canonical smiles of garlic acid. So we copy it, we paste it here, and we click on run. All right, so we run it, and after running it, we will have the result just uh, under uh, yeah, we will have our result just below, and we can actually see our results here. So it's from here, from this result, that we will apply that Lipinski's rule of five. Now, what does the Lipinski's rule of five means? What is it stating? Yeah, okay. Well, let's also bear in mind that all not all scientists actually accept this Lipinski's rule of five, because they have a different other arguments around the rule of five. But but we will be using that rule because it's still being used. And so what is it saying? So we just look on this thing on the net, and we will find it here. Components of the rule, Lipinski's rule of five. So Lipinski's rules uh, states that in general, an orally active drugs has no more than one violation of the following criteria. So there are essentially four criteria that the Lipinski's rules is uh, stating, and at the end, your metabolite, your molecule, should not violate more than one of the rules. And from there, you can say that, yeah, um, your compound is likely to be a drug. So the first one is there should be no more than five hydrogen bonds donors. No more than five hydrogen bonds donors. And the second one is saying that there should not be more than 10 hydrogen bond acceptors. So, and the third one is saying that the molecular mass or the molecular weight should be less than 500 daltons. Yeah, should be less than 500 daltons. And the last one is saying that the last one is actually the lipophilicity. Here they are saying octanol water partition coefficient, the log P. It should not exceed 5. That octanol water partition coefficient is just the lipophilicity of your compound. So those are the things that we will look into. So when we come back on our Swiss ADME database for our this particular compound, so if we look for the molecular weight first, so we have our molecular weight here. I will highlight it. So molecular weight, and this is the molecular weight of our compound, 170.12 Dalton gram per mole. So this one is less than 500. So the first rule or that rule is respected. So the molecule gallic acid, for the gallic acid, uh, in the Lipinski's rule, the molecular weight being 170.12 is less than 500. So is respecting the rule. So a second rule, number of hydrogen bond acceptor here. So our hydrogen bond acceptor here is 5, and the rule is saying that it should be less than 10. So that rule is also respected. Number of hydrogen bond acceptor. Now, just below that one, we will find the number of hydrogen bond donors, which is 4, and the rule is saying that it should be less than 5. It should be less than 5. So that rule is also respected. Now we are now looking for the lipophilicity. And the lipophilicity. So the log P. In this database, the log P that is generally considered is actually um, okay. You will find here that there are different log P, I log P, X log P. By pointing the cursor on the question mark, you will read about the definition and know what it states for. But what is generally used is the X log P3, the X log P3, this one. So this is that is what is generally used, and in our case is 0.770. But if you want, you can use the consensus log P 0.221, but i- the X log P3 is the one that is sorry, the X log P3 is the one that is generally actually used. So is 0. Our log P is 0.7. Yeah, lipophilicity. So which is also less than 5, because the rule is saying that it should be less than 5. So our Olympic skills rule in this particular case for this particular compound is respected. So the drug likeness is yes, this compound is likely to be a drug. So but even in this database, you can even find it where you can even find the drug likeness data immediately. Yeah. So you will find here drug likeness, and they are talking about the Lipinski, and they say yes. Yes means yes, the Lipinski's rule is respected, and they are saying zero violation. You see, right? So here our Lipinski's rule is respected. Is respected. So this compound, our gallic acid, is probably can be is likely a drug. So we can continue our study with that compound. So by the moment you fish out different metabolites of your plant, a lot of more than hundreds of metabolites, or around 100, and can even be more than that 100. So, and by the moment you start doing the drug likeness study by using the this database Swiss ADM, and leveraging on the Lipinski's rule of 5, or Pfizer's rule of 5. They also call it Pfizer's rule of 5, or simply the rule of 5. And by leveraging on that rule, and you can find out which compounds of your own database that you created, the metabolites, which compounds, which metabolites are likely to be a drug. So you can just use those specific metabolites, and to uh, uh to uh to fish out the targets in the Swiss target prediction now. Yeah. So that's what we were supposed to do first, even before finding out the targets uh, of the metabolites that will be likely to be a drug, which drug likeness is yes, according to Lipinski's rule. So that means if you are considering the Lipinski's rule to see the likeliness of your compound, the drug likeness of your compounds, that means you will discard the compounds that will not that will violate the Lipinski's rule. So that's what I wanted to actually add before we go on with looking into the different the common targets of uh, the two of our ailment and our plant. So the next thing we want to do now is to find our common our common targets. So we want to use any Venn tools that we can use. I think some people even use if you know how to draw a Venn diagram using Excel. So anything, any tools that you know that you can use to draw Venn diagram. But we will use this one and this platform right here. I will send all these links in the group also. So we will use this platform bioinformatics.psb ugents.be web tools Venn. So it's a bioinformatics platform that has different functionalities. For us, we are just interested in the Venn platform. So this is their Venn platform that they are offering, and you can actually read a bit about the platform and how to use it, the what and the how, and if you use their platform, they are asking you uh, to cite. Yeah, you can cite their work using their URL. So how to do this input section, you can either have files that you input and it will arrange it itself, or you just upload a list, so like a copy paste. That's what we will be doing right now. So our list, okay, so the output control, you can control your output here, but well, you can control your output here. So the Venn diagram shape, do you want it symmetric, non-symmetric, colored, no fill lines only? You can use it. You can use the one you want. But sometimes, if you have a lot of lists, a lot of groups, the symmetric might not work. So you might just need to use the non-symmetric one. Okay, let's go and do uh, net farm discuss. So we need our BSC database and we need MB targets. So BC database, we open it. We just want to copy all these things here from here. Go down. Shift, click, and we can copy everything. So this will be our first list. We come here in this on this platform and list one. We just paste, Control V, paste. If you like, you can enlarge this here. So Control V, and you can check if you don't have space, unnecessary space inside. So we have our genes well listed here. We can give it a name. The name we will give here will actually appear on the Venn diagram. So we can say BC. If I say BC, that means when I will be writing, I might need to state to tell the readers what the BC stand for breast cancer. So me, I want to put the BC there, and the next thing I want to put is, so we are opening the targets from the plants, Macaranga, battery, and we will copy. Shift click and we copy. Maybe come here and we paste. I will just delete the last unnecessary this thing there. So I will check this one also. And here I'm seeing that there are 3 genes on the same line. That's not a big deal. I will just list them. Enter, and it will go on the next line. So that's just it. Here, for example, I have 2 genes on the same line there, and same thing, and okay, yeah. Yeah. Okay, we are now good to go. So I will provide the name here, Macaranga bacteria. But there is a size problem with on this platform also. So by the moment I will write the whole Macaranga bacteria, after it will not show on the picture. So I can just write Macaranga, maybe B. Even this, I'm afraid that it will not show totally. Or I can still just write the initials MB. So I will need to define it when I will be writing. So after that, I will just come down for the output control. Venn diagram shape, I want it symmetric. Venn diagram fill, I want it colored. So I will just leave them like that. And I will come here on the submit button and I will just click. And let's see what it will give us. So this is the output that we are having. It will give you the list name, number of elements, unique elements of the different lists. Yeah. So overall number of unique elements. So what we are interested in is this. This is the diagram here. So we are having 19 common things. 19 common things for both parties. So what we are doing now is the test results here. We have the test results under here. So BCMB here is showing the 19 common things. This is what we are interested in. And then if you want, you can still see the genes for each batches BC and the MB listed there for you. So we can save this test results. We just click on save test results. We can open it, and this is what is actually giving us. Let's try and save it as okay. Let's save it as all files so that we might later be able to open it in Excel. Document net from this course. We open it. So our Venn, we say Venn diagram. Venn diagram. Okay, I can save it there. Or you can, if you want, you can just copy what we need. The 19. We just copy the 19 genes, common genes, and we create Excel file. We create Excel file. We create the Excel file. And alright. So this is our common genes or common targets. We will save it in our folder. Net farm discuss and our common target. So now we have our common targets, and we also need to save the image. This image is necessary if we are using it for later for publication. So we can save as PNG. So this is it. I will just go in the folder, copy it so that I can paste it back in our next farm discourse folder. The image. So this is the image that we now later use for our write-up. All right. So today we were able to, for now till now, so we were able to find different, um, the common target, both for our ailment, breast cancer, and then for our plant, from which we want to make a drug. So Macaranga bacteria here. So the next step now after this is to take the common genes. We will take the common genes into different other databases, and later on we will draw the protein-protein interaction network to find the core targets um, among these common um, targets. Yeah. So we will use the database called string, and we will later use the software cytoscape. So